In this session, we will be discussing special cases in Simplex method. There are 4 cases which we will be discussing one by one. So let me start with degeneracy. So when we talk about degeneracy, it says that one constraint is redundant. So you have seen that in LP model, we have various constraints, but any of the constraint is redundant, then this degeneracy can occur. So here, the point is when we are solving the problem using graphical method, we can find easily that a one particular constraint is redundant. Means even if I remove this, it is not going to change our optimal solution. But when we are solving the problem using simplex method, then how we can deal with it. So the point is that you remember we have optimality condition and the feasibility condition. Feasibility condition depends on the minimum non-negative ratio. So that is for the leaving variable. So if there is a tie at the minimum ratio, then what we do here is we choose the variable, the leaving variable arbitrarily. So in this case, sometimes what happens that one basic variable becomes 0 in the next iteration. So let us take an example now. We have a maximization problem subjected to 2 constraints. And in this particular problem, we know that it is a smaller than type, both the constraints. Then we are adding 2 select variable as x3 and x4. The objective function we have written by taking the right hand side into the left hand side and equals to the right hand side is now 0. Now everything is in the equation form. We can write in the simplex table. Now in this one, so since it is iteration number 0, we have written the simplex table now. All the coefficient corresponding to Z row, X3 and X4 row are given. And you know the reason why we have taken X3 and X4 as our initial basic solution. Now, since it is a maximization problem, you know that entering variable should be the corresponding to the most negative coefficient. So it should be X2. So once we have identified, yes, X2 is going to enter, then who is the leaving variable? So we will be finding the ratio. So 8 divided by 2, 4 divided by 2. Now look at the ratio. Ratio for both the variable X3 and X4, the ratio is 2. So there is a tie. That signifies that one of the constraint is redundant. So X2 is going to enter and X3 will leave. So for example, arbitrarily we choose X3 should leave. Now I am at the iteration number 1. Now iteration number 1, is there any for the non-basic variable, which is there any most negative coefficient? Yes, we have corresponding to X1. So X1 is going to enter and then we find a ratio X4 is going to leave. Now at this stage, there is no tie. And then finally we get the optimum solution. So what we will realize that since there was a tie, so it says that the one of the constraint is the redundant constraint in our formulation. Now here there is an interesting thing that now we get in iteration 1 and 2, we get the same optimal solution as X2 is 0 and X1 was a non-basic variable, so X1 was 0. Now in this case, when we move to iteration number 2, X1 has come into the table. So X1 and X2, so X2 is 2 and X1 is still 0, although it is 0, but it is basic. Now the objective function value is the same. So this is what you can see is the cyclic or this is a cyclic nature where you are moving from 1 to 2, but our optimum solution remains the same. And the value of a Z will also remain the same. Now question is, can I stop at iteration number 1? Because at iteration number 2, I'm going to get a same solution. So here, the answer is no, we cannot stop at iteration number 1. It is only because the simplex method says that Is there any entering non-basic variable at iteration number 1? Yes. Look at the iteration number 2. There is no entering variable. So therefore, we should not stop at 1. We should follow the steps which were defined with the simplex method. So at 1, it is called temporary degenerate case. Now, if we look at the degenerate case graphically, now you see that we have two constraints as given here, and our objective function is given like this. And this dashed line is showing the slope of this particular objective function. So you know that because this is a maximization problem from the origin, I will be moving away. Since I will be moving away, the optimum solution is given by this red dot, which is 0, 2. Now, looking at this figure, you know that even if you are going to remove this redundant constraint, optimum solution will remain the same. So what we are doing is, although we have two constraints, we are over determining the optimal solution. So that's why this redundant constraint has no role in the optimal solution. The second case is called alternate optima. Now, alternate optima can occur when the objective function is parallel to non-redundant binding constraint. So redundant we know because from the previous slide we can understand that if it is redundant, I can remove it. It is not going to change anything in optimal solution. But if it is non-redundant, it is an important constraint. Now, what do we mean by binding constraint here? A binding constraint can be defined as a constraint that is satisfied as an equation at the optimal solution. Now, finally, when we get the optimal solution, so you remember that the LP form is converted into the equation form so that I can use simplex method. And when I'm solving this simplex method and I get the optimum solution, so the slack variable or the surplus variable, if all of those variables are 0, so meaning that right hand side is equals to left hand side is equals to the right hand side. So that particular condition, I can say that a binding constraint is satisfied as an equation. I'm repeating again. Any constraint which is satisfied as an equation at the optimal solution means that the associated slack and surplus variable are 0 for that particular constraint. Let us understand this particular case by an example here. So we want to maximize it and we have two constraints. Now, if we draw this, so we get constraint 1 and a constraint 2 here. Now look at the equation of the objective function 2x1 plus 4x2 and look at the constraint equation number 1. Now, if you look at the slope, you can find that the slope of z is parallel to the constraint line 1. The same you can see in the figure that the dashed line is parallel to the constraint 1. In this case, what you will realize that the solution which are lying from point B to C, all of them will become the optimal solution for the given problem. Now, graphically, I can identify that the line is parallel to the non-redundant binding constraint. But how I can find it using simplex method? Let us solve the same problem. Now, here we have iteration number 0. We have written all the coefficient. It's a maximization problem. So we know that x2 is going to enter. Then we find the ratio. x3 is going to leave. After applying Gauss-Jordan operation, we get the in iteration 1, we get this particular solution, which is the optimal solution. Now what you will see that there is no entering variable. Since there is no entering variable, we have to stop it. And we get x1 and x4 value. Now here x1 is 5/2 and x2 is still the non-basic, means it is 0. So here we are going to get a point 5/2 and 0. Now suppose since x4 has a no role, just for calculation purpose, I am taking that x1 is entering and x4 is leaving. So in this case, what you will find that our objective function value will remain the same. However, the solution has been changed. Earlier, x1 earlier x2 was 5 by 2 and x1 0. And now we have x2 equal to 1 and x1 equals to 3. Now, what are these 2 points? So the first point is corresponding to the point B, and the another point is corresponding to the point C. So if I show you again, so since our objective function is parallel to our non-redundant binding constraint, all the solution which are lying on BC are optimal solution. We know that Simplex method identifies or calculates the corner point. So in iteration 1, it is already found the point B is optimal. Just for the sake, we perform one more iteration and we got another point solution C. And at both these points, our optimal Z value is the same, but the value of X1 and X2 are different. And that's why we call it as an alternate optima, meaning that we have the same Z optimal value, but X1 and X2 values are changed. So whenever this condition is arising, then we can say that this is an alternate optima. Now coming to the third case, which is unbounded solution. Unbounded solution means the objective function value keeps on improving infinitely without violating any constraint. So in this case, what is happening is that at least one of our variable is unbounded. That leads to this conclusion. So as and when unbounded solution is coming, it can tell our model is poorly constructed. So let us understand by this unbounded solution. So we have this example, we want to maximize our function and we have two constraints and the variable bounds. Now when we are going to draw the two constraints, so this is the constraint and the shaded region is our feasible search space. Since it is maximization, we remember that from the origin, we keep on moving away from it. Now look at this the equation of a Z. Now you can see that this particular region is unbounded because everything, if I'm going on the, in the above direction, in the upward direction, it is going to be feasible. And I am keep on moving this Z line, I will always get the optimum solution. So this means that I keep on changing. I will, since it is unbounded, so this Z value can go up to infinite. And that is what we have written, that the objective function value keeps on improving indefinitely without violating any constraint. And this is happening here in this particular case. Now this is quite clear from the graph, but when we are solving a problem using Simplex method, how we can understand. So here in the previous example, here we are adding a slack variable x3. Here we are adding a slack variable x4. So here we know x3 and x4, we have withdrawn the table. Since it is maximization problem, so -2 is going to enter, means x1 is going to enter, and based on the ratio, x3 is going to leave. Thereafter, in another iteration 1, x2 is going to enter and x4 is going to leave based on the Simplex method. Then finally, in iteration number 2, now if we see that still we have a negative coefficient in Z, so this means Z is going to leave. Now look at the non-negative ratio. So for this row, we will be dividing 20 divided by 0, which is infinite, means they are going to be parallel lines. 10 divided by -1, it is negative. So this we don't take it because our ratio should be non-negative. Now what is happening is that we have one variable x3, which is going to enter, but there is no leaving variable with us. As and when this condition is occurring, we can say that we have an unbounded problem. Again, we have an entering variable as per the Simplex step. However, there is no leaving variable based on the non-negative ratio. This suggests that the problem is unbounded. Now coming to the last case which is called infeasible solution. So we already know that the infeasible solution means any of the constraint is infeasible. We are the point is unable to solve one or many of the constraint. So the LP model with inconsistent constraint has no infeasible solution. Let us see that. So what is happening is, suppose when we have this kind of a constraint is smaller than type, then our basic feasible solution. So you remember that in the simplex method, we start from the origin. So our starting point, so the basic solution is always feasible. So this condition, when all constraints are smaller than type, the infeasibility will never come. But when we have other kind of a constraint, then this problem can come. It is only and now when we use these artificial variable, so these artificial variable are forced to become 0 at the optima if the model has feasible. Otherwise, at least one artificial variable will be positive in the optimum iteration. Meaning that when we are going to perform the simplex method, then in any of the iteration when we have to stop it, means the optima is reached based on the simplex rule, but the artificial one or many of the artificial variable are still basic solution, then we can say that it is an infeasible solution. Let us take an example now. We want to maximize this function and we have two constraints as given as smaller than type, another is greater than type. So let us assume that we are adding a slack variable x3. Here we are subtracting minus x4 plus artificial variable with this constraint. We are drawing this particular a simplex table for the iteration 0 after removing the inconsistency. So since it is maximization problem, I will be looking for the maximum positive, most negative. The most negative means that x2 is going to enter and based on the ratio x3 is going to leave. Now once we get it, now look at the Z row in iteration number 1. If we look at the coefficient of a Z, there is no coefficient which is negative. This means as per the simplex method, we reach the optima. But look at the basic variable. We have x2 and r. So r value is still positive, which is 4. Whenever there is any r in the simplex method as a basic in the optimum simplex table, this means that the solution is infeasible. So these are the 4 cases that we have to understand. The objective of discussing those 4 cases is when we are solving a problem using graphical method, it is easy to understand. But when we are solving a problem using simplex method, so we should know what are the conditions that will tell us that it is infeasible, degenerate, or unbounded problem, etc. Now I'm moving to the another section which is called sensitivity analysis. First of all, we have to understand what we mean by that. So sensitivity analysis means we are going to change the LP parameters. Those are called input parameters within the certain limits without altering the optima. So this means that we have x1 and x2 as decision variables, but the coefficients which are given in the LP, those are called LP parameter. So if you remember our first lecture where we discuss about the decision variable, we said that we have to identify all the parameters, and among all the parameters we will find who are the sensitive parameter that will become our variables. So x1 and x2 are variable and rest of them will become the parameter in the LP problem. Now the parameters are not usually exact. With the sensitivity analysis, we can ascertain the impact of this uncertainty on the quality of the optimal solution. So I will be discussing 2 cases now. So there are 2 cases. First is sensitivity of the optimal solution to the change in the availability of the resources. So basically we are talking about the right hand side of the constraint. Second is the sensitivity of optimal solution to the change in the unit profit or unit cost. So the cost coefficient. So let me take the example. Let me take the example related to the right hand side of the constraint. Suppose we are working in one of the industries where based on the raw material and the capacity of the machines, we have decided this is our optimal solution. So we made the LP model, we use Simplex method and we solve it. Now suppose at a one point of a time, so for example, during the heavy rainy seasons, we are unable to get the sufficient raw material or we are unable to use the machines in their full capacity. So when we are not going to get us a raw material, so this means the right hand side is changing. So when right hand side is changing, so we know that our optimal solution can change. Now the question is, if the right hand side is changing, so should I calculate the new optimum solution or can I find that impact using some analysis? So what this sensitivity analysis will do, that instead of resolving the problem, we can use sensitivity analysis and I can identify what will be the effect of changing the right hand side. Let me take another example on unit profit and unit cost. Now, suppose we have a one product, which is we have multiple products. That is, we are selling in the market as an industry, we are selling some products. Now, you know that there is a stiff competition in the market. Now, when we started our organization of this product, we decided that we are going to sell those products. So for example, mobiles. So when we take those mobile phone the first time in the market, the cost of those mobile phone are say 15,000, 10,000, 20,000 accordingly. Now, since the competition is large, at certain point of a time, you are thinking that instead of selling the mobile at 15,000, can I reduce to 14,000 or 13,500? So what I am doing, I am changing the objective function coefficient and at that time, I want to see what is the effect on my profit or on my cost. So these two examples, you can say that we are going to find the sensitivity of the solution with respect to the change in the resources or change in the unit profit or unit cost. So let us understand these two sensitivity analysis with respect to the graphical method. To understand that, we have taken one example here. So we have a one company called Jobco, which produces two products on two machines. A unit of product one required 2 hours on machine one and 1 hour on machine two. Similarly, product two, a unit requires 1 hour on machine one and 3 hours on machine two. The revenue per unit of product one and two are $30 and $20. The daily total daily processing time available for each machine is 8 hours. Now this is a problem statement given to us. Since we have already done LP modeling, we can immediately understand or we can immediately show the LP model. Now, as I said earlier, based on the revenue, so we want to maximize the revenue. So this is going to be our objective function. And we know that the price is revenues are given. This means our variable should be the number of unit of product one and a two. Accordingly, we can write our objective function and we can write our constraint. So for machine one, 2 hours for product one plus 1 hour for product two, it should be smaller than 8. Similarly, machine two we can write. So we have written the written the objective function and constraint and the variable bound. This is a two variable problem I can solve using graphical method. Now, if I use graphical method, I can draw the two constraints. I can find out the common feasible area, and you know that since it is a maximization problem, I will be moving away from the origin. When I'm moving away, so I can see that the point C is the optimal solution for the given problem. So X1 is 3.2, X2 is 1.6, and Z is 128. Now, as you remember that we will be looking for the sensitivity with respect to the right hand side, meaning that the machine one, the right hand side is 8, means the capacity is 8. If I increase this capacity from 8 to 9, what could be the change in X1, X2 and Z value, right? So here you can see the another equation. This is corresponding to the right hand side 9. Left hand side remains the same. Here, when we are changing the right hand side of the machine 1, or we can say constraint 1, let us identify what is the change in the Z. So before that, let us see these two equations. Now, when we are changing from 8 to 9, the optimal solution was C earlier. Now the new optimal solution will become G. So what we can say that when I am changing right hand side, X1 and X2 values are changing as well as Z are changing. So let us identify what is the rate of the change of Z. How I can identify this? This is I will be finding in the numerator the change in the Z value divided by the change in the capacity. So looking at the solution C and a G, I can find that numerator will be 142 minus 128 divided by 9 minus 8, which is 1. So it is $14 per hour. So this is the rate of revenue change resulting from increasing the machine 1 capacity by 1 hour. Now, what is this particular quantity is called? It is called unit worth of resources. Change in the optimal value per unit change in the availability of resources. It is also known as dual price. It is also known as shadow price. It is also used as a Lagrangian multiplier for the constraint. I'm redefining the thing. The unit worth of resources, dual price, shadow price, or Lagrangian multiplier, it is corresponding to the constraint. So here, so this means that for every constraint, there is a dual price. So for constraint 1, we have identified that there is a dual price. Now, second is the dual price 14 per hour remains valid for a change in a machine 1 capacity that moves its constraint parallel to itself to any point on the line segment BF. What we mean by that? Now this dual price 14, it has a range, means that if this rate will remain the same if I can change the right hand side within certain limit. What is that limit? So if I take this particular equation and if I start from point B and if I move up to point F, then this particular rate of the change of revenue per hour that will remain the same. This you can see from the line as well. So that is going to be the same. So that's why we have written the line segment BF. How we can find? Let us identify the minimum capacity of the machine 1 at a point B. So point B means this is what we are talking about. So the coordinate of a B, we found it. We can put into the constraint 1 equation. So this is constraint 1. So we get 2.67. Similarly, we can find the maximum machine 1 capacity at a point F, which is 80. Putting into the constraint equation number 1, we get 16. This means that if the machine capacity is ranging from 2.67 to 16 hour, the dual price will remain the same. However, if it is going outside of this range, then the dual price can change and then we have to recalculate it. It has a significance, we will see. I can do the same thing for the constraint number 2. Now you can see the constraint 2 is given here and I can vary this to the constraint number 2. So I have drawn this red line here. So can I find the range? Yes, we can find the range. So we know that this particular line, red line, I can move from point D to the point E. So let me take the minimum capacity, minimum machine 2 capacity at point D. So D is 040. I put this value in the constraint 2 equation. I get 4R. Similarly, I can take maximum machine 2 capacity at a point E, which is 80. put these 8 and 0 into the constraint 2 equation, I get 24. Meaning that the machine 2 capacity will be lying from 4 to 24. So within this range, the dual price for the constraint 2 is $2. Now in this particular slide, I did not show you how we calculate $2 per hour, but you follow the same concept that in constraint 2, if you change the right hand side by 1 unit, calculate the objective function again, then you know the formula and then you can get the dual price. So this dual price will remain valid when the machine 2 capacity is changing from 4 to 24. Let us have one brainstorming session. Now question 1 is, Jobco can increase the capacity of both machines. Which machine should receive the higher priority? Meaning that if I'm going to change the right hand side, that is the capacity for us. So then which machine is going to give me more profit? Now you are getting the idea that we already calculated the dual price, which says that the dual's price is positive and we increased one by one. Which one is going to give me the more profit or more revenue? So the dual price for machine 1 is 14. Dual price for machine 2 is 2. So we know that if I'm going to increase, say 1 hour for machine 1, I'm going to get $14 more revenue. So machine 1 should get the priority. Similarly, the same question can be asked in a different way, that suppose when we are going to increase the capacity, we have to pay additional. Why? Because when we are working for more than the capacity, we are going to pay to the operator, we are going to pay for the electricity and the other charges, etc. So these are the additional charges per hour. So is this advisable? So should I change the capacity because it incurs some additional cost? So now again, you are getting the idea that, okay, we have two machines. Let me identify their dual price. So the dual price for both the machine 14 and 2 is given to us. Now, since there is additional cost, so how much I'm going to get? So 14 minus 10 means I'm going to get I'm going to get $4 per hour with machine 1. But with machine 2, 2 minus 10 means it is going to be a loss for us. So this says that if we want to increase the capacity of machine 1, because it will even give me the revenue with respect to the additional cost. Let us have the third question, that if the capacity of a machine 1 is increased from 8 to 13 hours, how will this increase impact the optimum revenue? So since we are talking about the optimum revenue, we know that when we are changing the right hand side, our Z value will change. This is giving me an idea. If I can calculate the dual price of the machine 1, and then let me identify what is the range of the dual price in which it is valid. So we know that the dual price range of machine 1 is 2.67 to 16. Now 13 is coming inside it. So this means that dual price is valid. So let me identify what should be how much gain I'm going to get it. So you remember that the formula of dual price is numerator, there is a subtract divided by the denominator, which is the change in the right hand side. So if I take the denominator on the right hand side, so 14 into 13 minus 5 is the $70. So the revenue is increased by $70. And what will be the new Z value? So we have already calculated the revenue at the optimal solution C, which was 128 plus 70. So 198 will become our new revenue when we are changing the capacity of machine 1 from 8 to 13 hours. Let us have few more questions. Suppose that the capacity of a machine 1 is increased to 20 hours. How will this increase the impact? Again, we will see whether this 20 is coming into the range. So since the range is since 20 is outside of the range, it means that our dual price will change. Since dual price can change, so we have to recalculate the optimal solution and find out what is the Z, what is X1 and what is X2. Similarly, we know that the change in the optimum objective value equals dual price into the change in the resources. This is what we did. This is the same calculation in question number 3. So long as the change in the resources is within the feasible range. What about associated optimal values of variable? Now what we have done is when we are changing the right hand side, so we know right hand side of the constraint. So we know that the value of a Z is changing. And with the help of dual price, if it is lying within its limit, we can find what is the Z new value. And from the graphical solution, we know that point C was changed to point G. This means the X1 and X2 will definitely change. So in that case, we have to recalculate X1 and X2 when we are changing the right hand side of the constraint. So in the previous slides, I discussed about the change in the right hand side. Now I will be talking about change in the objective function. So I gave you an example of a mobile phone. Now this is the original problem, and we know that the optimum solution is lying at a point C, which is corresponding to X1, X2 value and Z value. Now question is, changes in the revenue units will change the slope of Z, meaning that if I'm going to change the coefficient of objective function, this is going to change my revenue. Now question is how we can change this revenue such that the optima will remain the same. Now look at the graph now. This is the Z equation, which is given as 3x1 plus 2x2. Now when I'm moving away from the origin, I get this is the optimum solution. The condition is that our optimum solution, which is X1 and X2, should not change, meaning that how we can ensure that the value of, say suppose I want to change 3 to something else and 2 to something else. It means that the slope of this line Z should lie between the slope of non-redundant binding constraint, which is machine 1 and a machine 2 constraints for us. So that's why I have written the line slope should lie between BF and a DE lines. So let us assume that we want to maximize and we have changed the coefficient. So C1 X1 plus C2 X2. C1 and C2 are objective coefficients. We can find the slope. So here we have two constraint equations. We can find the slope as 1 by 3 smaller than equal to C1 by C2. So this is the slope of objective function. This is the slope of machine 2. By simplifying it, I can get the value of C1 and a C2 here. So this gives me a range on the values. Let us have some few questions that will help us to understand the significance of the change in the objective function. Suppose that the unit revenues for a product 1 and 2 are changed to 35 and 25, very large value. Will the current optimum solution remain the same? How we can say, let us identify the slope. So here the new objective function will look like this. And if I find C1 by C2, it is 1.4. Now you remember that the range of this slope should be lying between 0.333 to 2. 1.4 is lying. This means that yes, our optimum solution will remain the same. What will change? Only Z will change. So optimum solution, as I go back, the optimum solution means X1 and X2 value will remain the same. If I put into this X1 and X2 value, I can get a new revenue here. Let us take the second question. Suppose that the unit revenue of product 2 is fixed at its current value at 20. What is the associated range of C1? The unit revenue of product 1 that will keep the optimum unchanged, means the point C which we get, that should not change. C2 we have fixed. So what could be the range on C1? It is easy. Why? Because C2 is given. I know the range 1 by 3 smaller than equal to C1 by C2 smaller than equal to 2. I can put a value of a C2 20. So I can say that C1 will be lying C 6.67 and 40. This range is only valid when C2 is 20. Similarly, we can get the range. So this is the optimality range of a C1 when C2 is fixed to 20. Can I find the same optimality range for C2? Yes. Let us fix C1 to 30. If I'm fixing it, then I can get a C2 range. Now you have to note down, if when I'm fixing the value of a C2, I can get a one range of C1. If I change the value of a C2 to say 10, this range will change. So this you should understand it. So with this understanding of the special cases and the graphical understanding of the sensitivity analysis, I'm concluding this session.